Yes, hi everyone. Sorry for the technical issues. My name is Tamer. I'm a physicist. I'm very excited to be giving this talk today. Let me share my screen here. So today I will talk about quantum parallelism, which is a little piece, a little aspect that comes into play into a few quantum algorithms. Um, so this is the outline of the talk. I'll give a little bit of a context first, and then I'll do a very quick review of the basics. And then I will talk about quantum parallelism. We will start really digging into it, and then we'll look at the two algorithms which very clearly take advantage of that aspect and achieve actually some parallel computations. Okay, so quantum computing is a very exciting new area. Maybe it's not really that new now. It has the potential for a huge improvement in computational ability if we can really achieve it. So there is a lot of advances that need to be done on the theoretical and on the experimental side, but a lot has been achieved so far. There's there's algorithms in all kinds of areas that have been kind of figured out, and experimentally there's a lot of different machines, quantum computers that have actually been built from different kinds of technologies. Okay, so quantum parallelism, what does it really mean? So it just means, it's a very simple thing. It just means that if you have a computation and you want to, if you have, for example, a function and the question is, can you evaluate that function for different arguments at the same time in one computation? So it's not like classical parallel computing where you actually send the computation to two different processes, to each of them do a separate computation. But here in this case, it's just one computation, really one computation, which will give you the answer to both evaluations of that function. Two or more, of course. Two. Okay, so let's do a quick review, and I'll start with a little analogy here. So suppose you have a question. In this case, you have a computational question. It's very difficult, and you can't really solve it on the biggest supercomputers you have. And suppose down the street, maybe there's this huge office of very smart people who are happy to help, and they can actually help. And you can even help them help you. So you can even give them instructions on how to do that computation. And they are very capable, and they have huge resources, as we'll see. So the only thing is that for you to get their answer, you have to pass by through this person sitting at a desk.
Tamer, sorry to interrupt. Your voice is a little bit low. People are asking if you can speak a little bit louder.
Okay, let me try something here. Is this any better? Is this any better? No.
There's a slight hum in the background.
Oh, is it the hum? Okay. All right. I'll try.
Do you have an earphone or headphones that you can use, Tamer?
Let me just see. No, I don't. I don't think. No, I don't think it will have one that works with this. Is the hum? Okay. If I speak like this, is it better or no? I can raise my voice, but I'm not sure if it's going to help.
Yeah, can someone comment in the chat? Yeah, okay, raising voice is good. They're able to hear you.
Okay, sounds good. All right, I'll raise my voice then. Okay, so so let me go back to the presentation. Okay, so suppose you have a question, and it's a computational question that you're trying to answer. And you have a group of people that can help you, but the problem is, in order for you to get any information from them, that person at the desk has to first summarize it and then give you just a summary of their answer. Okay, so this is an analogy to quantum computation, which I'm hoping you will be able to pick up as the presentation goes along. So let's start with a little bit of a background here. Okay, so how do we describe objects in quantum systems or any quantum object? It's usually described with what we call a quantum state. So that quantum state is just a vector that lives in like something similar to your usual coordinate space here. Let me bring my pointer. So you have an x and a y, where you have two basis vectors, I and j. And any vector in this state can be described by a combination of a little bit of I and a little bit of j. And so things that are similar in that any state in a quantum system can be described this way. And instead of calling this just a space, it's called the Hilbert space. So it's denoted, for example, by this notation, the psi, and it's similar to a vector in this space. And now your basis vectors, instead of being I and j, are now 0 and 1, for example, in the case of a qubit, where a qubit is a quantum object which has only two states. Okay, so if you want to look at the dynamics of how things change in a quantum system, all of the changes in a quantum system happen through these unitary transformations. And mathematically, they look kind of, you can represent them as matrices, and they do rotations in the space of our vector. So if our vector was here, psi, then u of psi will just move it in a rotation around some axis. Okay, so we'll see a bit of a few of these unitary transforms as the talk goes on. Okay, now the fun part. Okay, so now we've looked in the previous slide at a qubit, so an object which has two states. But now if you want to look at two qubits, your Hilbert space all of a sudden expands, and it's no longer just two-dimensional. Now it's four-dimensional. So now your Hilbert space is described by these basis vectors for the case of a two-qubit system. So 0, 0, 0, 1, 1, 0, 1, 1. And they each denote, each one of them, I'm trying to, this is a kind of like a sketch of how you would project a four-dimensional space on screen. Maybe it's not the best representation, but each of these states here, like for example, the 0, 0, this says that the first particle in the is in the zero state, and second particle is in the zero state. This state here, first particle is in the zero state, second particle is in the first state, in the one state. Okay, so and so all of a sudden now we've expanded from a two-dimensional Hilbert space to a four-dimensional Hilbert space when we added one more particle. If we go to a three-qubit system, now it's an eight-dimensional space. So really the space expands as 2 to the n. So we can very easily think as we have maybe 10 particles. It's already a big system. If we have 50 particles, as we have already some quantum computers today with 50 particles, it's a very huge system. I think, if I remember correctly, with 50 particles, you're already at the number of particles in the universe. Okay. So, okay, so if we have a system of so many particles, let's say this many particles as there's digits in this state, then you can one of the basis states, for example, or any state can be represented as such a state. So this is similar to a classical bit sequence, right? So if your state is this, it's very similar to a classical bit sequence, you know. This sequence can represent, for example, a number or a character, and so you can manipulate it to do computation. But now the interesting thing with quantum computing is that states can not just be in this kind of state, but it can also be in superposition of many of these kinds, and it looks like this. So you just add up a few of these vectors, and then see what your resultant vector is, and it's a superposition of so many different basis states. And this is actually one of the things that gives it a lot of that gives quantum computing a lot of richness. And of course, dot 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 here means that you can add as many basis states as you want, as many basis states in your Hilbert space, right? And finally here, just some notation here. When you look at the system of more than one particle, the notation here is to write that the state is either in 0, 1 here means first particle is in 0 state, second particle is in 1 state. So you can write it this way, where you separate the cats, or very explicitly here, where you show that this is a tensor product. This is what it's really called, of these two single particle states. Okay. Okay, so then comes measurement. So in quantum, measurement is treated very differently from everything I've described so far. So if you have such a state that, such as the one I've been describing, and you perform a measurement into it, so all of a sudden it's gonna collapse into one of these basis states. So you no longer have this quantum superposition, which is the quantum magic. Now it goes back to being along one of these basis states, right? So it's gonna go just like that. It's gonna go here, and so it's gonna go into one of the basis states. We don't know which one for sure, but we know the probability of it going either to this basis state, that one, or this one, or this one. And the probability is just given by these amplitudes. You just take the square or the norm squared of it. Oh, by the way, I didn't mention, it's not really relevant in this talk, but these amplitudes here are complex numbers. They're not just real numbers, but it's a very small detail at this point here. I don't think it's going to be relevant to this talk, but it's something to know. Okay, so let's start to look at the actual quantum parallelism. Can we actually get a quantum computer to do two computations at the same time or more? Okay, so suppose you have a function here. So this is a function that takes in real numbers, gives you back a real number. But now to simplify things, because we're doing computation, everything is in binary. So this function is going to be just a binary function. So it makes things much more easier. We're going to be looking at a function which takes in just either a 0 or 1, and can give you a 0 or a 1. By the way, I just meant to first check for questions before I move, and also check for the sound issue.
Sure, Tamer, there are 2 questions from Rishi. And the first question is superposition similar to linear combination of vectors? And are basis states similar to basis vectors in linear algebra? Those are the questions that we have from Rishi.
Yes, and the answer is yes to both of them. And let me just go back here. So so this is what I'm trying to show here. Think of them exactly as that. You think of them that you are in a vector space. Either you think of it in linear algebra, or you think of it as in just like a geometry space here, coordinates. So yes, and a superposition is just exactly that. It's a linear combination of your basis states. So yes. Any more questions?
That's all we have right now. Rishi, does that answer your question? You can type it in the yeah. Okay, perfect. Thanks. All right, we're good to go.
Good. All right, so we're going to take this binary function, and it's the very simplest function we can think of for a 1 qubit that we can do operations on. And so let's start with this and see whether we can actually get some parallelization. Okay, so actually, if you have such a function, there's really only four possibilities for such a function. You can have f of x equals to x, or not x. So the not here is the logical not, which takes the 0 into 1 and the 1 into 0. And, or you can think of it as 1 minus x if you like. Or you can have the constant functions if it's either 0, just 1, or just 0 here. Okay? So how can we implement this function in a quantum circuit? So it turns out that if you try to do it with one qubit, it's not going to really work, because for these constant functions, the f of x equals to 0 or f of x equals to 1, if your input is okay, so you always need your functions in quantum computing to be reversible. That means if I tell you the input, you can calculate the output, but if I also tell you the output, you can always go back to the input. So that means that the same number of inputs have to be equal to the number of outputs, and that also means that if the function is constant, so you cannot reverse it and get back what was the input that gave you that output. So that's why we have to add here more qubits. So this is a quantum gate. It's again, it's one of these unitary. It implements one of these unitary transformations that I talked about, but it needs two qubits now, not just one. This x is going to going to be like the argument of our function, but we need an extra input variable y, which we need, but we don't really need to evaluate the f of x, but it needs to be there for the transformation to be reversible. Okay, and so this pattern you'll see in many gates or in many quantum circuits is that when you have an input x, it often goes back out the output. So it's called usually a control qubit. So this is how our function is going to look like. So the question is, what is this u? I should also add that this plus with a round circle is an addition modulo 2. It's just or you can think of it as an XOR. So when the two inputs are similar, it gives a 0, but when they're different, it gives a 1. Okay. So I'll just refer to it as plus from now on. It's just easier to just say it this way. Okay, so let's look at how to implement this for the function for the case where f of x equals to 0, right? We only have 4 cases, so let's see actually how we can implement it for a bunch of them. So if our input states are either 0 and 1, so the basis states that we were talking about, then we want to make sure that u performs this. The output, so what does this mean here? There's two cats, that means there's two states in the output. Sorry, it's a two-particle state, right? So two particle in, two particle out, right? Quantum computation preserves information, doesn't throw away any of your qubits. So so we want that the output qubit look like this: an x for the first one and a y plus f of x in the second one. But so in our case here, in this example, f of x is 0, so you're just wind up with x and y, which is the same as what your input is. So in the case of f of x equals to 0, what is inside this box is actually nothing. It's just as if you had two straight wires. So it's the identity. It just takes your input and gives it back to you as an output. Okay. And if you similarly look at f of x equals to 1, you'll notice that your circuit inside of this box is just an identity on the first qubit and a x gate, which does the not function, which does the negation on the second qubit. Okay. And you can also verify that this is what the matrix of the U transformation looks like for the case of f of x equals to x and f of x equals to not x. Anyways, I'm just the point here is to say that we can always find, in this case, a unitary transformation that will implement this f of x using that kind of circuit that I showed. So yeah, in this case, the circuits will look like this. This is a C-NOT gate, and this is a C-NOT gate here, sandwiched between two NOT gates on the first qubit. By the way, sometimes the NOT gates is just denoted by the X gate, or sometimes it's just written like this. Okay, so this is how we implement f of x quantumly. Your inputs are here, and this is what comes out when you plug in your basis states. Okay, so now let's use this circuit. Let's set some inputs that are going to help us achieve quantum parallelism. Okay, the first input here is what we're going to plug in into this second bit here is just the zero state. Okay, and in the first state, we're going to use a superposition. And this is where all the magic comes when you do superpositions in quantum circuits. Okay, so then the question is, we saw above in the previous slides how you get your output qubits when you have basis state as input. The question is, how do you compute f of x, or how do you implement this u when this is your input state, a superposition? Okay. So the answer is simple. Because quantum mechanics is linear, and because any vector can be described as a sum of different basis vectors, you can simply compute what the function does to your basis states and then add them up to get what it does to your superposition. So if we want to know what our function does to this 0 plus 1 state, then we're going to, sorry, it's not a 0 plus 1. So it's a 0 plus 1 tensored into 0, right? So if you want to know what it does to this state, I think I should have written it on this slide, then we just compute what it does to the 0, 0 state, and then compute what it does to the 1, 0 state, and then add them up. So this is the addition here. So u of 0, 0 plus u of 1, 0 is going to be this term plus this term. And so, and then you can, see that this is your state here, which was our input state. So a superposition tensored with a 0. So this is the first qubit, and this is the second qubit, and this is the sum here. So the square root of 2 here is to make sure that the length of our state is 1. That's always the case in a quantum state in this Hilbert space, is always length 1. Okay. All right, so this is our output state here. And if you look at it, you can see in something interesting here. You can see an f of 0, and you can see an f of 1. So they're both present in our output state. But the question is this useful, right? So here's the thing. If you remember what I mentioned about measurement, if you try to measure the state, what's going to happen is it's going to collapse into either this green state here or into this yellow state. So if you measured the two qubits, you'll either get 0 f of 0 or 1 f of 1. So let's say you get 0 f of 0, then you have no idea what f of 1 is because it's lost. Remember, this measurement, just collapses the vector onto one of the basis states, and you lose all the information of what it used to be before that collapse. Okay. So, so this is what I just said. So we have to be a little bit more clever in order for us to extract this information. We cannot simply just plug in the superposition and get out a, both answers. Okay. So any questions at this point?
I don't see any questions right now, so I think we're good.
All right. Okay. So just keep sending in the questions. We're going to have a couple of pauses during the lectures, and then we're going to have more questions at the end. Okay. So Deutsch's algorithm is one of these clever algorithms where we're going to try to get around this fact of, measurement kind of destroying everything, and this is how it's implemented. So the question is, in order for you to get some information, you have to, despite the fact that measurement destroys a lot of information, you have to kind of look for a question to ask, which can be answered by a certain arrangement of your circuit or of your input qubits. Okay. So in this case here, we're going to try to compare two global properties of f of x. So the global property, what does it mean? It means that it's a property of the function which you cannot know from evaluating the function at just one point. So if you want to know whether our function falls into this category or this category, you have to classically evaluate it at both 0 and 1. So if you want to know whether your function is one of these constants, f of 0 is equal to f of 1, or one of these non-constants, if f of 0 is not f of 1, there's no other way but to evaluate it at both f of 0 and f of 1. So we'll see here that it's possible to know it in one computation, to know whether our function is in this class or in this class. Okay. All right. So it's exactly the same circuit as we've seen before. That's going to implement our function f. And we're going to change just one thing. We're just going to change the fact that now our input of y is different. So, and that's going to help us answer that very specific question again. So again, notice that the question had to be tailored to answer this, to make use of parallelism. Okay. In some textbooks, you'll see an extra gate H here, which helps with the clarification, but it's not really necessary. Oh, I should also say that a lot of this discussion I got from Nielsen and Chuang textbook. So if you want to go back and look at this principle in more details, probably you'll find it there. Okay. So I should also say, so these are your inputs, and if your quantum computing machine only has 0 and 1 as your input, as what it can prepare for your initial states, then you would need this H transformation. It's another unitary transformation, and it does this. It takes your 0 and takes it to this 0 plus 1 state, and it takes the 1 and takes it to the 0 minus 1 state. It's a very common gate used in a lot of quantum circuitry. Okay, so this is, I'm just taking a step back from where I was in the previous slide and saying, if you want to prepare those states, you just use those Hadamard gates. Okay, so let's look at this circuit step by step. At each point, after each operation, after each gate, we look at what our state looks like. So in the beginning, it's 0 and 1. So this is our state, 0 tensor 1. And then we apply the Hadamard gates, and we get this. So 0 plus 1 tensored into 0 minus 1. Oh, so the interesting thing now is that the tensor is it's very similar to multiplication. You can just expand out these two terms. So 0, 0, 0, 1, 1, 0, and 1, 1. And the signs are going to be crucial here. Okay. So what will the output look like? So like we did in the previous section, in the previous part of the talk, we're going to just evaluate it for each of these basis states, because that's what we know how to do. So for each one of these, the first qubit is your x. These are just the labels for our gate here. So the first qubit is an x, and the second qubit is the y. And we compute what it is for each of these basis states, and then we add up the result and get our final state. Okay, so if you plug in a 0, 0, what we're supposed to get is 0 for the first qubit, that's x, and then for the second qubit, it's going to be 0 plus f of 0, right? But 0 plus something is just that something, so it's just f of 0 for the second qubit. Same thing here is going to be, this is our x is 0, so we have 0 here again. And for the second qubit, we have y, which is 1. So 1 plus f of 0, right? So 1 plus something modulo 2 is just the opposite of that something, the not of the negation of that something. So 1 plus f of 0 is not f of 0, negation of f of 0, and is denoted by this bar here. Okay, so if f of 0 is 0, then the second qubit here is in 1 state. And similarly, you can do this for the other input states, and this is your end result. Notice that the signs are still here with us, right? Because this is just a transformation on the superposition, so everything is linear. We end up with the same signs here. Okay. So now our task is to look to see if we can if this state can help us differentiate between two cases. Is f of x of this type, or is it of this type? Is it a constant, or is it not a constant? Okay, so let's look at this output state and look at what it's going to look like for the case of f of 0 equals f of 1, and for the case of where it's not constant. Okay. So if f of 0 is equal to f of 1, what we're going to have here is we're going to be able to group together terms where f of 0 is equal to f of 1, right? So in this case here, f of 0 is equal to f of 1, so we can group the first and the third term, and f of 0 naught is equal also to f of 1 naught, because we negated equal terms, so they're going to be the same. So we can group together the second and the fourth terms. So that's what I'm going to do here. I'm going to group together those terms. So if we group together the first and the third term, this is what we get here: 0 and 1 transferred into f of 0, and the same thing for the third and the second and the fourth term. Okay, so this 0 plus 1 is, we've seen this before, it's actually called the plus state. I didn't mention that. So it's a plus state. It's just, you can actually measure a plus state. It's just, you can do the measurement in a different basis. This is something I should have mentioned. So instead of measuring in the, let's say this is our original basis 0 and 1, 0 and 1, we can rotate the basis and measure into a different basis, okay? So, so this 0 plus 1 state is what we have here on the first qubit, and it turns out that we have it on the second term of the superposition as well. So we have the plus on both these terms, so we can factor it out. So we have plus on the first qubit transferred into this superposition on the second qubit, right? So let's look at the superposition. What does it say here? So f of 0 and and not f of 0. So if f of 0 is 0, then f of 0 is 1. And if f of 0 is 1, then f of 0 is 0. What I mean to say is that this state is always going to be 0 minus 1, state 0 minus state 1, up to a minus sign, right? Because it just depends on whether f of 0 is 0 or 1, okay? So it's going to just look like this. It's either plus or minus depending on f of 0, and it's 0, -1 in both cases. So this is our final, like the most simplified version of this output state. It's a plus state tensored into this. Actually, this is a minus state. I could have written it as a minus as well. Okay, so we can do the same thing for this other case here, and then the only difference is going to be that we're going to group together different terms, and it's going to matter because all these signs are different. So in the end, if you do the math, you're going to find that it's actually going to be different on the first qubit, but the same thing for the second qubit. But that's a good thing. We have one particle which is different from in this case versus that case, which is the first qubit. And if we measure that qubit in this plus or minus basis, then we should be able to tell whether our function is one of these or one of these. Okay, so problem solved. We have let me go back here. We have made one measurement of the qubits we have, and based on that measurement, we were able to know something that would have taken us to computation on a classical computer, namely that f of x is either constant or not constant. All right. Okay, yeah, so now is a good time to take questions. Is there any questions? Let me see here. Explain again which types of function amenable to quantum parallelism. Okay, so so I've taken a shortcut. I mean, I've taken the simplest possible function here, which is any function which takes in a 1 bit of information, 0 or 1, and gives us back 1 bit, 0 or 1. And then we'll see later that we're going to generalize this to a function which takes in so many bits, but still gives us 1 bit as an output. And the question is, I'm not aware of, it's not very easy for me to see how you can combine all of the this result and the next result I'm going to talk about to apply it to a general function. It might be possible. It might be along the same line of how you build large functions on your classical computer from just operations on single bits. Okay, but so far we're just looking at the simplest function. Oh, textbook in the chat. Okay, I'll have to write it after the talk. Okay, just remind me again, please, if I forget. All right. Okay, so the next generalization to this algorithm, and let me just, I'll be right back. Give me a second here. Sorry about that. Okay, so the next generalization in looking at this type of parallelization is to look at the Deutsch-Jozsa algorithm, which now, instead of taking in 1 bit, 1 qubit as your input, or okay, let's talk about the function. So when we're talking about the function, we're talking in the classical realm, a function will not take in a superposition. A function will take in either 0 or 1. That's the function from the previous section. And now we're going to generalize this to a function which takes in as many zeros and ones as you want to give it. Let's say a number n of bits. And then, but it's still going to input just 1 bit of information. And again, these are your input. These qubits are going to represent our input state. And this is going to be our output as given by the same x. If we put in x as our basis states here, if these were just basis states in the input, then we would get them back here. And our output here is going to be, again, the same form here, y plus f of x modulo 2. Okay. So it's the next step. It's the next generalization where the input is now bigger, can be as big as you want, but the output is still one qubit. Okay. So like we did in the previous part, we can't just do parallelism any way we want it. The crucial part here is that in this algorithm is that they found uh, something which you can, if you wanted to know about a global property of the function, which can be evaluated in one measurement or one computation. Okay, so, and that question is similar to the previous one, is just a generalization of the previous case of the Deutsch algorithm, and it's whether the function f of x is a constant function, so whether it's just gives you the same output regardless of the input. It doesn't matter if it's a 0 or 1. So whether it's a constant or whether it's what they term as balanced, which is we have the same number of zeros and ones in the output if we look at all the possible inputs, right? So again, it's a very contrived problem, but it demonstrates what we're looking for. So, and you can see here that it's kind of a generalization of just this 2 qubits case, right? Okay, and so this is what the circuit looks like. It's the same kind of U. So you would be able to find the right circuitry inside of that black box if you know your f of x. So you would be able to represent f of x with a U. And these are, and the same as we had before, these are the Hadamard gates, which are going to prepare our states as similar to how they were in the one input case, right? So again, let's look at the circuit step by step, and now we have the extra complication of having to deal with many qubits, right? So instead of having just 2 qubits like in the previous section, now we have so many input qubits, which is like, by input I mean the x variable, so these guys here. And then we have one y qubit, so that's what my label here does. So this is the first qubit, second qubit, that's the label 1 and 2 here, and then dot dot dot, there are so many qubits and qubits. And so I'm going to keep in the following, I'm going to keep the y qubit separate, and then I'm going to just label it by y. At some point, the label is going to drop. But so this is our state here. Okay, so like we did in the previous section, we need to expand out these this product, right? So you have many of these terms. Each one of them is the same. Looks like a 0 state plus 1, and then you have n state like this. So in order to expand out the product, you just go normal product rule. I can't remember what it's called. So 0, 0, 0, 0, 0 is going to be your first term. So we're just multiplying out the first 0 in each of these terms. And then the second term is going to be 0, 0, 0, 0, and then 1 from the last qubit, and so on. So you're going to have this superposition of all possible combination of n zeros and ones. Okay. So that's for this part of the input, and then the y, I'm just going to leave it as it is for now. Okay. So I'm going to rewrite this huge sum. So this is a huge sum which has 2 to the n parts. And so I'm going to rewrite it as the sum over x. And now x is a label which stands for what's inside of the cat, right? Okay. So and then I'm going to take each of these. This is just a simplification in the notation, right? So I didn't really do anything by rewriting it this So, and then I'm going to take this x, and then I multiply it by the two states that I have here in the y qubit. Right? So it's going to be x0 and x1 with a minus sign in the middle. Okay. All right. So let's look at what u does to this. So the output of this u. So this is our state from the previous slide. And what is u going to do to the state, right? So again, like we did in the previous section, we're gonna look at the effect of u on each basis state. And by the way, x here is a basis state, right? Because it's made up of just each x in the sum is either is made up of just one basis vector. It just happens to be a long vector because we have many particles, okay? Many qubits. Okay. So again, we're gonna look at what u does to x and 0. So again, it leaves the x the same, and then for the y bit, the qubit, it just adds f of x, right? And so again, f of x is so f is defined on that large set of zeros and ones. So we are having the right size argument if you think in programming terms. So x does take in, sorry, f of x does indeed take in this kind of x that we've encoded here. So again, so we have a 0 plus f here and 1 plus f of x here. Again, that means that 0 plus f of x is just f of x, and 1 plus f of x is f of x not, or not f of x. Okay. So this is what I just mentioned. And finally, we're going to factor out the x here and be left with this. Oh, not finally, because there's more steps. So what does this term mean? It just means that, again, this is going to be either a 0 or a 1, and it's going to depend on what f of x is, right? So f of that particular x, right? So we have so many x's that this sum is going to run through. And so for each one of these f of x, the sign of this term is going to be determined by minus 1 to the f, right? So here, minus 1 to the f, so if f is 0, minus 1 to the 0 is plus, is a positive plus 1. And if it's f is 1, then minus 1 to the 1 is a negative. It gives us a negative number. So this minus 1 to the number is often used to kind of like as a shortcut for the sign is going to depend on the parity on whether your f is even or odd. Okay, and so this is our final state. It's just a sum of these x states with different signs depending on f of x, and then the y state is just a minus state. Okay, for all of them. So you can even factor it out. You can think of this sum as the first qubit, and this is the second qubit. Okay. So again, let's look at those two classes, the constant class and the balanced class, and see whether when we plug in those values, whether we can differentiate our output state, which I'm going to denote by psi out here, depending on whether f belongs to this group or this group. Okay, so let's look at the constant case first. What is this? So this is all of, so if f of x is constant, it's going to be either 0 or 1. So that's going to make this term either a plus 1 or a minus 1. And so we can just take it out of the sum. And then the sum is going to be a summation of all our basis states, right? So remember, we've seen this before. Let me just go back here. We've seen this before here. This is the summation of all our basis states. And it's equal to just the plus state on each qubit, right? So this is this is how I want to simplify it next. It's just the plus state on each qubit. So, okay, so this is a bit confusing, not the best notation here. This is not the same x as here. This x here is not the same as x. So the x here just refers to our input register, all of these input qubits, whereas here it was like our dummy variable for the summation, and it referred to precisely, it referred to basis states. Okay, so what I mean by plus here is that all or of our x input states, sorry, our x output states are in the plus state individually. Each one of them is in the plus state, right? And then minus y is the same. Okay, so that's the more straightforward one to compute. So let's look now at the balanced case. And so I'm going to take a hint from this result and from the previous result, and I'm going to just show that if these two are distinguishable, then maybe they're distinguishable because the vector of the psi out is perpendicular to this psi out here. So the psi out in this case is going to be orthogonal to this case. So if it is orthogonal, then when you do a measurement and your vector collapses on one of the bases, you're gonna be able to distinguish between those two cases, right? Okay, so if we look, so how do we figure out whether two states are orthogonal or perpendicular? So think again in the geometry example, you just take the dot. If you take the dot product between two vectors and they're perpendicular, their dot product is zero. Okay, so this is the notation here for a dot product. It's just known as an inner product between those two states in our Hilbert space. Okay, so what I'm going to do is I'm going to take the dot product between the output that we get from a balanced f of x and this x vector here. Okay, and I'm going to also not worry about the y. So I'm going to take the dot product of this part in the balanced case with the state plus on all the x on all the x qubits, right? So the x qubits are the ones that go from 1 to n. Okay. So what is x? So we have psi out. We have the form for psi out, and that's this part here. And then what is the plus state? Well, it's just the summation of all the x's, right? It's just now that I'm using a different dummy variable because now I have x here, so I wanted to use something different. So I'm going to use x prime here. Okay, so this is the summation of all the basis states, similar to this guy here, which came from the summation of all the basis states. Okay, so how do we compute this big product here? So you can just turn it into a double sum, right? So the summation of everything inside over both x prime and x, and then you're going to take advantage of the dot product between this x prime and this x. So what is x prime and x? Again, they are basis states. So think of your I and your j, right? And so x prime and x, this dot product is only going to be non-zero. It's only going to be non-zero if x prime is equal to x. And in all other cases, it's just going to be 0. So if x prime equals to x, so that's, for example, the state 0, 0, 0, dotted with the state 0, 0, 0. So remember, that's a dot product between the same two unit vectors. So that gives us a 1, right? So we only have to worry about running the sum on one of the dummy variables, let's say x, right? And then x prime and x is just equal to 1, so it's going to disappear, right? So our sum is just the summation of all these minus 1s to the f of x. And because our f of x is balanced, so we have the same number of 1s and 0s as output of f of x, this sum over all possible x's is going to give us 0. Okay, so it's a little bit it's a bunch of math here. So, but in the end, it's 0. Okay, so what does this mean? It means that if we look at psi out that comes from the balanced case and psi out that comes from the constant case, they are orthogonal to each other. So let's say so if they are orthogonal, so let's now look at the measurement that we can make. If we measure the first qubit, for example, in the plus state, we're going to get, sorry, we're not going to just measure the first qubit, we're going to measure all of the qubits. So if you measure all of the qubits in the plus state, and you find, in this case here, in the case of f is constant, you're guaranteed that all of them, 100% of the time, are going to be in the plus state. So if you measure in the plus minus basis, you're always going to get plus for all of them. So what does it mean for a state to be perpendicular to this all plus state? It just means that at least one of the states is going to be in the minus state. Okay? At least, sorry, I'm not being precise here. So at least one of the qubits is going to be in the minus state. So again, you measure all of the qubits, and you find that if you find that at least one of them is not plus, then you know that you are, in this case here, in the balanced case. Okay? Okay, so any question on this part? Or actually, let me just summarize, and then we'll take questions on this last part and on everything else. Okay, so basically what I've shown here is that you can take a quantum circuit which represents a function, and you can evaluate global properties of that function in one computation. To do that, we had to ask a very contrived question in this case, and that's how we were able to get our answer. So it's not going to work for any problem that you have, but the trick here, as is the trick of developing all these quantum computing algorithms, is to find the right question to ask, one question where you're going to be able to access everything, all the richness of the linear part of quantum mechanics. So again, if we go back to that analogy with that big office with so many people helping you out, the measurement is that person sitting on the desk. It just makes you lose a lot of information. So the trick is to find a way to distill all of the information in the large Hilbert space, which is the big office with the people helping you, in such a way that you get the piece of information that you want, even if it's a much smaller data than that was in the Hilbert space. Okay, so that's everything that I wanted to say. I also should mention that we used superposition and interference to get to our results. So superposition is the case where those states were in the superposition states we talked about, and interference is when these pluses and minus made things cancel out. Okay, and so that's all that I wanted to say, and I'm happy to take questions.
Thanks, Tamer. Yes, we do have a couple of questions. If you can check Q&A, okay. We have about 7 questions.
Oh, okay. So I'm gonna put the answer to the name of the book in the chat.
Sure.
Okay. So where's the chat? Oh, chat is here. Oh, here's the chat. So wait, I'm having a hard time finding the chat window.
We can also send the participants a message later on with the link.
Okay.
So if you want to take on the next questions, we can.
All right. Okay. Let's see. Can we map the problem of f of x being constant or balanced to real world situation? Probably not. It's a very contrived problem. But if you do come across a situation where this would be very helpful, then you have one way to solve it, which is very efficient. Okay, Deutsch's algorithm seems to work because of some happy accidental correspondence between a characteristic of the input and the output. Is it possible that this happy accident phenomenon is the reason why we have so few, so few quantum algorithms? So no one knows, but it is possible. So, and then as far as I know, I don't think, okay, as far as I know, I cannot say the answer to this is no. But as far as I know, it is quite possible that this kind of happy accident is indeed why you get this to work out. But then your problem or your task is to look for other happy accidents. For example, Shor's algorithm, which kind of finds the two factors of large numbers very efficiently in polynomial time, is one such happy accident. So people work very hard to find the algorithms that let us solve these useful or these relevant problems. Okay, I hope I answered the question. But if not, please send again a follow-up or a clarification. So Kareem, I have a question about the design of the quantum algorithm. How to be sure that when we measure it, we collapse the right risk. Oh, so so the question is, how do you make sure that when you design a quantum algorithm, it collapses to the right answer? And that's the entire endeavor of finding the right algorithms to tackle your problem. So there is no one way. I think every algorithm is going to be different. You're going to have to use, as far as we know now, principles of superposition, interference. Shor's algorithm even uses a lot of things that are not even relevant to quantum mechanics. It just uses things, I think, from number theory. So everything that you can use to find a clever way to answer some question is the way to go about it. There's no one single way to do this. There's no one single way to do it. The U is an N control one. The U is the N control. Okay. I'm not sure I understand the Helen's question. The U is the N control.
I think the question was asked when you were presenting at a point, so it could be out of context right now.
It's an answer to a question. Okay.
Yeah.
Okay. Okay. In another word, how to design a quantum algorithm. Okay. So I think I answered this one. Why can we solve these algorithms on a classical computer? Is it just a matter of speed? Okay. So this is a good question. I think I might not have clarified this. So the idea here is to find quantum computing algorithms which allows us to solve very difficult problems, right? So by difficult problems, let's say you have a computational problem, and as you scale the input, the size of your input, the number of steps that you need to do to solve that problem grows exponentially as the number of input bits, let's say bits, right? Let's think in a classical computer, right? So the idea, what people are trying to do in quantum computing is now they want to look for quantum computing algorithms which will solve the same problems, but instead of it growing exponentially with the number of inputs, it's going to grow more slowly than exponentially, right? So Shor's algorithm is one such case where it's the number. So okay, so when you want to do factoring, which is you take a huge number and you want to look for its factor, if that number is very big in terms of the digits of that number, then it's going to be exponentially. It's going to take exponentially many more steps for you to factor it, and that's why all of our password encryption is based on that principle. Okay, but in Shor's algorithm, which is a quantum computing algorithm, it's no longer exponential. The number of steps are no longer exponentially rising with the number of inputs. And so this is what we're always looking for. So in this case here of quantum parallelism, we decreased the number of steps. So in the case of, in the case of n input qubits, let's say the later part, the Deutsch algorithm, we had n inputs into our gate. So in a classical computer, if you wanted to find out whether this function is constant or not, you would have to go at least through half of these bits and measure and measure them. Sorry, you have to go through half of these x possibilities and plug them into f and see whether what you get back is the same or not. So if once you go past half of them, right, then and let's say they've all been the same value, 0, then you know that now your function is constant. Okay, so you had to do n/2 computation to know whether your constant is your function is constant or not. Okay, but in this quantum algorithm, you only had to do one computation. So the speed up is by factor of n, right? Or n/2. So this is what we're always looking for: a quantum algorithm which will decrease the number of steps that you need to do to solve a particular problem. Okay. Will the slides be posted? That's a question for Amalak. Amalak,
for sure we can post the slides and also the recording. In a week or so, we'll put the recording on YouTube, and the slides, after you send that to me, Tamer, I'll post it on our website as well.
Okay, I'm happy to do that.
Perfect, thanks.
Okay, so Helen says that someone asks, so the generalization is basic, the end control with one not gate.
I think this was also in context to one of the slides.
Yes, so I think they are referring to this. So yes, we're going to generalize the n control qubits to n instead of just 1, but keep this y qubit to just 1. Is there a general algorithm for finding the difference between all states are in the 0 value? Oh, that is, can you tell the difference between a pure state and an, okay, so so a mixed state is not what you described here. A mixed state is another discussion. So I think what you mean here is there a way to tell the difference between a 0, and whether there is a superposition? So the way to do that, so the difference between a basis state and a superposition state, you can tell the difference if you do more measurement. You have to do more measurements. In one measurement, you cannot tell the difference. And if you do more measurements, then, like we said, the state is going to collapse on either one or the other, with the probabilities being given by the amplitude in front of each basis state. So if it's in the case of a plus state, 0 and 1, so 0 and 1, they were both divided by the square root of 2, 0 plus 1, and divided by the square root of 2. So actually, you square that square root, that 1 over square root of 2, and the probability for for measuring each one of these guys is just 1/2. So you do a bunch of them, a bunch of measurements, and hopefully you're not so unlucky that after 5 or 10 measurements, you at least see that you have one. Um, so you have more than one of these basis states show up in your measurement. Okay, I hope that was clear. If not, please send another question. Okay, now I guess up to now we've learned about how quantum computing works in parallel for specific kinds of f of x. Could you give an example of how quantum computing works in parallel for an arbitrary f of x, which gets input from? Okay, I see. This is what I said earlier. I'm not sure if this particular example is generalizable to this case where you have n inputs and n outputs. I'm not sure of that, but if you are asking whether whether quantum algorithms exist for things that are more useful than this very contrived problem, then the answer is yes. But then the difficulty, there is still some difficulty in actually finding good algorithms for useful applications, right? How to know whether the question to quantum to QC is right? How to know whether? I'm not sure what Itamar means here. How to know whether the question to QC? How to know? I guess whether pursuing the development of quantum computing is the right thing to do or not. So actually, there are voices that there are some opinions that say that in the end you'll find that quantum computing is going to be not really useful for anything. It's not. You're going to find out that somehow quantum mechanics doesn't allow you to do the kind of computations that you want to do. But because we have things like the Shor algorithm, which takes a very difficult problem and solves it to a simpler problem, we are very tempted to go out and find more quantum computing algorithms for other practical applications. For example, think about chemistry. So chemistry is based on quantum mechanics, and when two molecules or atoms or more than two, when it gets more complicated, when they interact, so it's very hard to keep track of that problem on a classical computer because of exactly what I mentioned, that your Hilbert space grows up exponentially with the number of particles that are interacting. So here in quantum computing, we have access to that Hilbert space. So everyone is trying to see, okay, let's try to map this problem in chemistry to the Hilbert space of our quantum computer and see whether we can actually make that computation. And this is a great deck of slides. Are you going to share them? Yes, we will make them. We will share them. Okay, thanks from Hirishi, and you're welcome. I really liked your analogy about the help desk and being able to answer one question at a time. The idea of quantum parallelism, does it mean conceptually would be an office in theory be able to? I'm not sure about what you mean by ahead of time and predictive. It's just what it allows you to do is that what quantum computing and what quantum parallelism allows you to do is just decrease the number of computations And what a lot of researchers are trying to do is find algorithms which are going to decrease that number of computation by a lot. So that's what we want to do. So I don't know if you're thinking of machine learning in terms of predictive ability. So machine learning is another application which people are trying to implement on quantum computers, or find algorithms, quantum algorithms that implement them. And so if that, and there is a lot of advance in that area, but yeah, if that area advances, then yes, you can do machine learning on, you would be able to do machine learning on quantum computers and do the predictive, the type of predictions that you do with machine learning in general. Okay, on your example of finding factors of a big number, how could we input the 32-bit text using just a few available qubits? Okay, so I should clarify, the algorithm, the Shor's algorithm, was developed before any quantum computer was ever built. So it was developed just in theory. The algorithm exists. The math is there to tell you that if you have a quantum computer, you with the right number of bits, then you can do the factoring that you want. So the highest number now of qubits in a computer is that in two places, in IBM and in IBM and Google, where they have roughly around 50 qubits, and so around but they're very noisy in both cases. I don't think they can implement Shor's algorithm on 50 bits. They might be able to do it on a fewer number of bits. So yes, so the existence of the algorithm doesn't mean that that the hardware to implement it actually does exist. Okay, so the algorithm exists theoretically. Okay, example. Oh, for example, high complexity question. So, high complexity question to quantum computing to solve. Yes, so that's so Itamar is just clarifying on his or her question. Does it mean, so is quantum computing able to solve? If I understand correctly, they're saying that is quantum computing the right way to solve high complexity computational questions? And there are some, like in the case of Shor algorithm, and we're looking for more. People are looking for more cases of such algorithms. Okay. Is it possible to get a list of all questions asked along the webinar recording? Okay. Some of the questions. Oh, I'm sorry. I should have read the questions out loud. Amalak, are the questions available for everyone, or is it just for the presenter?
No, I think it's only for the panelists.
Okay.
If interested, Rishi, send us an email. We can send you the questions, but the recording will have all the questions and answers.
Okay. Talking about chemistry, which you just spoke about in terms of the number of interactions, is there a possible application for quantum computing in vaccine research? Oh, yes. In the future, hopefully, yes, because this is definitely one of the applications that's being targeted by, or that's being thought about right now for quantum computing researchers. And it's very relevant because in the end, vaccine or any medicine is just an interaction between some chemicals and some biological cells or parts in your body, right? So if it's chemistry, then yes, the idea is, yes, we hope that quantum computing is going to provide a way to solve chemical problems. Now the trick is which chemical problems, right? If it's like an inorganic problem where you have where you just want to see how two atoms interact, and maybe each atom has like 20-ish electrons, so your number of your Hilbert space is going to be 2 to the 20, which is huge still, but at least hopefully you can answer that kind of problem with 20-ish qubits, right? But if you're talking now biology, now we have to kind of step back and think, okay, now the interaction is between very big molecules, maybe, or maybe you're going to want to think about an interaction between, a very large system. And so your quantum computer, the number of qubits in your quantum computers have to scale and match this kind, the number of particles or electrons. In chemistry, it's mostly done by electrons, right? So you have to match the number of electrons, right? So if you have one I don't know, sodium atom, so I think that's 11 electrons, right? So the number of electrons is big. Okay, and of course, what I meant to say is that your Hilbert space grows as 2 to the number of interacting particles, so that's even bigger. Okay. Oh yes, okay. So yeah, okay. This is the biggest problem in the world. Yeah. So, but okay. So the answer is yes in the future, but not. But hopefully, we will find an answer for COVID before we are able to answer it with a quantum computer. But yes, in the distant future, for future problems that we might have, hopefully, that's going to be one avenue to solve these problems. Definitely. Okay. So it looks like that's all the questions that we have here.
That is correct. And I looked at the chat as well. I think that's all we have.
All right. Okay, so the one last thing I will do is for the person who is asking for the book. It's by Nielsen and Chuang, and I will edit my slide to include that because I should always put my references in. And thank you all for coming.